Okay, I think we're hot here. Thank you very much, Dune. First off, I'm going to do a quick poll to illustrate kind of where we are. How many people here actually work for the GARS Directorate? You'll notice it's half the people. So those of you who don't, pick one person that just put their hand up and go up to them afterwards and ask if Gerry talked about what they did. If they didn't, ask them. It's an incredibly diverse directorate, and I cannot possibly in 40 minutes talk about everything that's going on. So I've tried to illustrate kind of what we do with the selections that we've made. The folks from my directorate know a little bit about me. I've been in the National Lab System or associated with it since 1976. Jimmy Carter was elected to the White House the day after I started at Pacific Northwest National Lab. So I know a little bit about the Department of Energy. And in fact, the job I had last before I left the Northwest was kind of comparable to the job that Jim Misevich and Reinhold Mann combined have. The basic research portfolio of Northwest is relatively small. So it's not surprising that coming to Brookhaven, which has got such a strong basic science tradition, that I'm kind of the applied science guy. And I'd like to put that in context today. There are going to be plenty of opportunities for questions at the end. I'm going to try to bop through here. This clock is 33 or 30 minutes slow, but I'm not going to use that one to gauge what's going on. So let's get started. I'm going to talk about the strategy. I'm going to talk a little bit about our work in non-proliferation and related research, and then talk a little bit about our energy portfolio, focusing on the grid, solar, and storage. And I'm going to try to motivate these along the way because I think it's the motivation for both the existence of the directorate and the sort of things we do that's important to know about us. So basically, this is something I used 2 weeks ago in the strategy retreat with the Policy Council that said we're really kind of the applied research arm. And the whole goal here is motivated to, as Dune said, to increase societal impact and to grow the research base. There's always something, it's always a question about growing the research base, and I think Suzanne talked about that a little bit in her talk later on. We're kind of a $700 million laboratory in $1 billion suit of clothes, and in order to have the earnings or the overhead that's necessary in order to support the lab, we need to be a little bit larger. And as Dune said, this is not just an internal desire for growth's sake. This is something that the Office of Science thinks is incredibly important for two dimensions. One, for generating the kind of support we need to have to make the laboratory and improve it, but also to increase our impact. And hopefully the things I've chosen will do that. The GARS Directorate was created as part of the Blueprint Project to help catalyze this effort. We're not exclusively responsible for growth, but the traditional set of customers we have are the ones that we're looking to grow with. So the picture that I started drawing early on about what we tried to do is it said, well, we have some basic research assets up here, the BES assets, and I guess I can use this pointer, and the then environment and life sciences assets. And we were talking about kind of this technology push versus market pull. This is a classic discussion that takes place in industry. Just prior to coming here, I had the opportunity to work in Asia for a while, and it's one of the classic problems that universities and national labs in Japan and Korea and China talk about all the time. But I think that it's a little bit weak for what we do here, because the Department of Energy is a mission-oriented agency. And on the science side, we talk about scientific grand challenges and significant scientific questions. One of the projects that I helped get started was the atmospheric radiation measurement program in the Office of Biological and Environmental Research. And the compelling question of how do you put together a set of models to get the clouds of the right kind in the right place for the right reasons into a climate model so that you might in fact be able to successfully predict what the response to carbon dioxide was kind of the underlying scientific question we dealt with. On the applied side, I think we worry about compelling societal needs, and the needs we try to address in GARS come from the challenges of energy and non-proliferation. And as Dune's pointed out, these are two of the significant missions of the Department of Energy. So I'm going to start off with non-proliferation and national security. We've discovered that most of the time when we talk about that, it's always at the end of the list. And so I'm not going to do that this time. I'm going to put it up at the start. Basically, what we do here at Brookhaven is to help detect and deter nuclear proliferation by countries or terrorists. That's the mission that we're tied to. And the lab and the folks that have been here have a tradition that goes back to the dawn of the laboratory in providing exactly that kind of support. We've added terrorists to that dimension more recently, but proliferation among countries is in fact an important concern. So what do? Basically, we support a variety of things. One of those is diplomacy itself. You know, the whole idea is to figure out how to convince other governments to not develop nuclear weapons, the classic non-proliferation mission. And then we also try to negotiate treaties to commit people not to proliferate or to help anybody else do that along the way. So what do? What are the critical questions if you're going to go in and convince somebody not to do something is to know exactly what they're doing. And so this is a component of intelligence associated with that. And for example, what does the US government need to know if it's going to have a non-proliferation conversation with Iran? That's a fundamental societal question that you have to understand if you're going to move forward. I happen to have the opportunity to be in Seoul when the North Koreans set off their first nuclear weapon. So proliferation kind of was up close and personal during that period of time. The second thing is their national government actions. And I think one of the interesting things about this is we think we have a problem with following procedures when it comes to safety. Imagine what you're trying to do when you're trying to protect the materials that can be used for weapons of mass destruction from being disseminated. It seems on the surface to be very simple things, right? Provide security fences, walled up windows. But these are the basics, but they have to be done perfectly. This is not a mistake that results in a slip, trip, or fall. This is a mistake that results in someone getting a hold of material that could be used to our detriment. And we also carry out training on how to protect facilities from, for example, disgruntled workers who might steal nuclear material. There was a period of time following the fall of the former Soviet Union where the weapons designers were not being paid. In order to understand disgruntlement, you can kind of think through that, and they had a very marketable skill during that period of time. In terms of international coordination, as we all know from the discussions, actually I think this is the 10th anniversary of the start of the Second Iraq War, a lot of conversation about the IAEA, and basically what we try to do is, and we're involved heavily during the period of time of how do you provide experts and equipment for use in inspections. We actually train inspectors here. We train other country officials on how they're carried out, why they need to do this, what is the nature of the safeguards that we're in fact putting in place. And it turns out to be incredibly important. I saw there are several people in the room here that are involved in precisely that activity. And if you go back and look at the history of the period of time following the first Iraq War, where controls were systematically turned off, and that was part of the concern that was going on. The next is that the IAEA is incredibly important. There's what's called the Nuclear Suppliers Group, where there's a collective action to try to prevent materials from falling into the hands of the wrong people. And then there are the global security partnerships, where we've in fact tried to, and even this one goes back into the 90s, tried to get people who are involved in the weapons complex in the former Soviet Union, Kazakhstan, Russia itself, involved in other work. And there was a program actually run not only by the Department of Energy, but another early one called SABIT, run by the Department of Commerce, where we actually brought scientists in. And I remember one of the best cloud physicists we had out at Pacific Northwest was a Russian that came from the Institute for Applied Optics in Tomsk. And he couldn't tell me what he used to do, but radiative transfer is pretty important for a lot of things. So I think that kind of covers the big picture. But what happens if folks get through and the weapons of mass destruction and the materials get here? Our role then transitions to what happens with RAP. We have the Radiological Assistance Program, and we try to help determine if a threat's coming out, whether it's nuclear or not. That's our specific assignment. So what happens is people like Kathleen McIntyre and her team and head off to major events. They get to go to the inauguration, they get to go to the conventions, they get to go to the World Series and stand outside in the cold not seeing anything to be on call in case some incident, in fact, begins to develop and then help assess the threats that come from that. We also train first responders who might have to deal with a nuclear or radiological event. And in fact, our experts, and you can see some of them here, were actually sent to Japan in the post-Fukushima era. So it kind of draws a picture around the kind of activities we do. It's kind of the soup to nuts of non-proliferation and dealing with the consequences of a failure in non-proliferation when we get to the role of the RAP team. Behind this is a number of technologies. One of the ones that I promised to talk a little bit about discovery to deployment that we're particularly proud of is the work that Ralph James and his group have done on high sensitivity room temperature radiation detectors. They have a broad set of applications here, and one of those, and probably best to do it here, where we talk about here's foundational work done under support of the National Nuclear Security Agency, a number of cooperative agreements, and then finally the translation to industry is to the medical industry itself, where this helps with prostate diagnosis. As you note here, we're working with the folks at Gamma Pharmaceuticals, I think they're called now, but originally Hybridyne, to figure out how it might be applied to other forms of cancer detection. So that kind of talks about the non-proliferation piece. It's a significant mission. It's a critical societal need. Those of you who've heard me talk before, have heard me say that the national labs, part of it is spinning reserve against time of national emergency. That's kind of the lesson we learned from World War II. And there are two emergencies that exist right now in the United States. One is the threat of proliferation that we talked about here, and the other is the preparation of this country for the 21st century. But right now it's barely suitable for the 20th century, so that we have a big gap we have to fill in that regard. God doggone, at any rate. So the picture that we talk about when we talk about discovery to deployment is one that looks like this. It's kind of a buildup of the one that we talked about before. And we built much of this vision around energy. It's got broader applicability, but I'm going to come back to this model along the way, that we have these fundamental capabilities that come out of basic energy sciences. We have the research and research results that really provide the seeds of solutions. Similarly, we have these needs and demands that come from industry or come from the government itself. In a very real sense, the detector development we have, one of the principal customers is not necessarily the medical industry, but the non-proliferation industry itself. So these are governmental use, private sector use. And we'll talk about these items down here, but this little box right there, those three words are probably the thing that I've discovered over the years is most important if you want to have impact, is that you have to be mindful of what, in fact, the use is going to be. There are a lot of nifty things that you can turn around and develop, but if you're not mindful who's going to be using them, it's very difficult to create impact. So basically, we call that mindfulness, this is the buzzword, market back, and they drive our programs in a lot of ways. A number of the programs are, in fact, and I'll touch on a number of these, are tied to the facilities. And I think that prior to my arrival, the work that happened in high-temperature superconductors, where in the materials group and Peter Johnson and company, they developed high-temperature superconductors. We're still a leader in that particular area, but we not only developed the technology that allowed us to get better, higher and higher critical currents and at higher and higher temperatures, but we also helped develop the manufacturing technique that allowed the cables to be produced that could be used. And so there are cables just down the island here that, in fact, were created using the technology developed here at Brookhaven. And one of the projects I'm not going to talk about in detail is one that Pat Looney is leading with the Photovoltaic Manufacturing Consortium, which is based up near Albany, where they're trying to understand how to improve the manufacturing of thin film photovoltaics. This is a particular technology that the United States and NREL have settled on as their path forward, and they've invested in tremendous facilities in the Albany area, led by Semitech, in order to improve that capability and retain some sort of photovoltaic manufacturer in the United States. So those speak to the customer partnerships we have here, and that's one of the places that we interact. So basically, the strategy in energy is what I'll call market-backed, starting with the state of New York. The fact of the matter is we do not have a big part in the DOE applied research portfolio. I think our biggest portion of that actually is the work we do for the part we do for the Nuclear Regulatory Commission is bigger than any of the other applied programs that we have inside of the laboratory. However, we're the only multi-program laboratory in the Northeast, which has got 20% of the country's population. And some of the most pressing grid problems and energy problems are extant here. Congestion, aging infrastructure. And so we put our strategy together and said, well, since we're not a big player up here, maybe we have to convince these folks that we're valuable by solving problems here in New York State. So that's kind of the picture. This is New York State's energy. It's a little old, but it's kind of nice. Here's the amount of energy that this is the amount of energy that gets generated from petroleum, natural gas, coal, and other fuels. Jim Misevich puts this in a green box because he says we're the greenest state in the nation. We have only 6.4% of the population and only use 4.1% of the energy. It actually, our energy use pattern looks far more European than it does, than it looks like the middle part of the United States, for example. So when I first arrived here, I think it was within just a couple of weeks, Pat Looney and I were asked to help with a plan that would allow the state of New York to reduce its greenhouse gas emissions 80% below 1990 levels by 2050. And this resulted in a plan that's yet to be adopted in the state, and I'll show you in a little bit why that's the case. But basically, when we got done, we kind of looked ahead and said, well, what are the problems we have to worry about? One is, what's the role of nuclear or carbon dioxide capture and storage? This is the decarbonization of central generation. The mission here, the emission reductions desire cannot all be satisfied with renewables from within the state. What was the reliability and capacity of the grid, particularly in the face of increased electrification, and what role would biomass play? And basically the scenario that was put together was one for a very robust economy. This is important to say because, in fact, the state of New York met the goals of the Kyoto Protocol, not that they signed up, but their carbon dioxide reductions were consistent with that what thought would be required from the United States. That was accomplished by exporting industry, not by reducing emissions or more efficiency. We just took the industry that we had at the time of the Montreal Protocol, and they weren't around anymore, and so the carbon emissions went with them. So we had actually a model that grew the industrial base, and again, the requirement was that the renewable energy, as much as possible, come from within the state, which is a job-building activity. And so that was seen as the critical goals. And then geology caught up with us. So this picture is one that when I used to run the Joint Global Change Research Institute at the University of Maryland, we used a lot. And let me describe a little bit what's going on. So this is what we're worried about in climate change. The atmosphere in 2004 contained, this is 800 gigatons of carbon. Scientific units kind of interchange both ways. So that's the size of the bar. And the problem that you've got is that we're in the process of taking these things that have been under the surface of the Earth for millions of years and putting them up there. And that increases the carbon dioxide concentration and therefore has an impact on climate through a complicated set of interactions. We also point out that there's only 500 gigatons of carbon in biomass. So even if you double the amount of trees, you're not going to fix this problem in a big way. Actually, the best thing to do is plant grass, as it turns out, because that's what makes soil. And so the more interesting thing is this right here, is that so these are all roughly proportional to the size of the reservoir we're talking about. This whole black thing here is unconventional fossil fuels. This is tar sands, tight gas, shale gas, all that sort of stuff. And lo and behold, what's happened? Shale gas in the state and elsewhere, we're in the midst of what we euphemistically call the dash to gas. It's not an unreasonable thing to do. Gas puts out roughly 20% of the amount of carbon dioxide that you would have from burning coal, for example. So it is, in fact, could be a transitional fuel. But as we move to gas, there's an expansion of the infrastructure, power, residence, commercial buildings, even vehicles. And the important part about this is, I don't know how many people have noticed the increase in pipelines blowing up around things. An entire highway was blown up in West Virginia. There was a major one in San Diego. An entire block was destroyed in Mexico not too long ago. This is not an infrastructure that one can allow to get to the condition of the current electrical infrastructure. It's incredibly dangerous. It has to be put in place. And what happens is that as you start putting it in buildings and your residences, and I'm a firm believer that the only way to cook food's with natural gas, but the fact of the matter is you can't capture the carbon from that. So these diffuse sources, in fact, turn out to be very important along the way. And as we make the dash to gas, the extent to which these diffuse sources of carbon will be a barrier to achieving the 80% goal is something we've kind of urged the state to look at. So that being said, we still have focused very much on a low carbon future. Science and technology for the electric infrastructure, sustainable chemical conversions. This is the way the plan for the Office of Science is organized. And we think the outcomes of each of these thrust areas are important both nationally as well as internationally as well. And so what I'm going to do now is focus a little bit on this guy up here. Saying that, recall that I've said that the state of New York is our primary focal point. We have a lot of great assets here. There's NYSERDA is one of the most highest regarded state institutions in the United States for its investment in energy research. There's the Energy Storage Consortium, there's the Smart Grid Consortium, there's a little enterprise called the New York Energy Policy Institute, and there are a tremendous number of industrial and university in the state that have a history of cooperation. This is far greater than the cooperation that I saw amongst universities and industries in the Northwest. It's far greater than the cooperation I saw in Japan. It's close to what you see in Korea and China, but there it's mandated as opposed to being kind of out of self-motivation in the process. It's extraordinary, and we combine that with our assets to kind of take on these challenges that we talk about. So I'm going to talk about the electric system. So, and I'm going to do it on the grid because this turns out to be pretty important to us. It was declared the greatest engineering accomplishment of the 20th century by the National Academy of Engineering. The North American grid is the world's largest machine in that context. And all it does is just match electricity supply and demand everywhere all the time. And that's what's so remarkable about it. Now we have to change this grid. It's old, it's falling apart, it doesn't have necessarily good controls on it. We're changing the nature of the energy source that drives it, so we got a problem. So by analogy, what we're talking about doing is turning a DC-3 into a 747 while fully loaded with passengers without landing. I mean, that's kind of what we're trying to do. We have to continue to satisfy the demands while transforming at the same time. It's not a trivial thing to do. And how many people deal regularly with utility companies other than paying their bill? They're very conservative enterprises in the way in which they operate. And it's not surprising. We talk a lot about safety. The early monopolies in electricity were allowed because it was perceived, quite rightly, that electricity is a very dangerous substance. And having too many people kind of trying to supply electricity was not seen as a public good. And so the early creation of those monopolies kind of came from that process. So the smart grid is, we talk about the smart grid, how is it impacting? There are lots of definitions of the smart grid. I used to have a slide that listed them all, but it got to be 4 slides and it wasn't very useful anymore. But the fact of the matter is the grid's already pretty smart. It does, so you go and your little lights flicker. That's because the feeder's going out to you, and all of a sudden they're bringing your electricity in some other way. This happens more or less automatically in a lot of ways. So what's making it smarter is the increase of information that can be collected and used to manage. And this results presumably in improved reliability and resilience, better efficiency, more rapid recovery, all that sort of jazz. Those are the goals. That's the set of holy grails. So our vision here is to begin with, and this may seem a little peculiar to talk about a geospatially referenced grid, but most utilities consider their grid to be a circuit diagram. And in fact, the connection between that and a map is fairly rare. How many people remember reading that when the people came from all around to help the recovery after Sandy, they were handed paper maps? They were not handed an iPad that says, go here, do that, here's the sort of thing that goes on. And part of this disconnect of the geography of the grid from the electrical connectivity of the grid. And we believe making that reunification is important. The other nifty thing is that B&L is a federal enclave, and we have, with the indulgence of the Electric Safety Committee, the opportunity to use equipment here on this site where we judge it to be safe prior to commercial deployment, which is of tremendous value. And so basically we want to use this perspective, this asset, in order to investigate renewable integration and penetration, how we affect distribution efficiency and reliability. And I'm going to talk a little bit about microgrids in a moment. And so the idea is to create kind of a trusted real-world simulation center where we can study this transformation to take place. Notice, to contrast what I do. Whoa, I didn't want to do, oh, there we go. Contrast this with non-proliferation. This is all aspirational. All that non-proliferation stuff we're doing, we've been doing it for 50 years. We'd like to be able to look back 50 years from now and talk about this transformation that we're talking about here. The heart of this is a collaboration with Stony Brook called SGrid 3. It involves some construction over there and a facility here. Here on site, we talk about AEGIS, the Advanced Electric Grid Innovation and Support Center. And our focus here is on the distribution system. Out in the West, one of the big problems they have is the transmission system. And that's because the generation assets and the people that use electricity are separated a great deal by geography. One of the big jobs in the Western Interconnect is take all the power that comes from the hydro facilities in Canada and ship it to Los Angeles. I mean, this is 1,500 miles of stuff that kind of picks up every ambient current in the atmosphere and wiggles and flops and does all kinds of things. Here in the that's, by the way, that's the 2003 blackout right there. That's, if you look at the lights at night, and that's from space, that's kind of what North Korea looks like during that period of time. And one might argue that our grid is kind of contemporaneous with that. So, but at any rate, so the idea is to try to figure out, use this facility here to move forward. Concurrently with that, we have the asset of the Long Island Solar Farm. And I don't know how many people saw the Newsday article that talked about Paul Kalb. Paul is the leader of a project in collaboration, I think, with NCAR to try to figure out how to do forecasting in order to be able to do this. And we'll see the importance of forecasting in a minute. But it's very well designed. And one of the cool things, and I found personally satisfying, the problem in the East is that clouds, these are bad things when it comes to managing one of these things. And it turns out through the ARM program, you have a bunch of people whose whole goal is to figure out how to visualize clouds and predict what kind of clouds are going to be present in a particular location. This is a smaller scale than a climate model, but it's the same basic folks that are involved in that process. So basically, what historically has happened is, imagine the grid as I described it to start off with. We've got people want to use electricity here, and they turn things off and on, and they run their thing, and they come home at night and turn on the oven, and the lights go on, and air conditioning. And then over here you've got your nuclear plant or your coal-fired power plant, and so you've got a unpredictable or a demand that you have to predict, but you've got a relatively reliable supply. The problem with renewables is there is a tremendous amount of variability in renewable energy, wind and solar being the primary examples. So basically, here's the wind resource down here. The load up there, that yellow thing, that's the variability of that. And one might argue that the match between supply and demand became worse as a result of putting the wind into the system. So you're faced with this problem, therefore, of forecasting not only the load, but forecasting the supply as well. Because what you have to do is you have to have other assets that will allow you to fill in and do that exact match that you need to have. And I think I finally come up with a way to describe the consequence of not having that exact match in the following way. I was recently in a hotel, and I was on the top floor, in the top floor room, the furthest from where the hot water heater was. All right? So every time anybody along the line turned on their hot water or turned off their cold, it changed the temperature of the water in my room. That's what happens with the grid. That if you're sitting out in Montauk and all of a sudden somebody's having a big party in East Hampton and decides they're going to cool down the entire environment by keeping their doors open, there's a demand that lowers the amount of voltage that is in fact coming to you. And that change, in the sense of your hot water going away, doesn't just make you cold, it shuts down the grid in order to protect your appliances and things like that as well. So that's the problem if you don't match supply and demand. So what they talk about doing is firming up power through generation and storage, and they start talking about what they call ramp rate requirements, that if you're going to generate solar or you're going to generate wind, you can only change how much power you're providing according to a particular rate. So many energy units per unit time change. So what we've decided, this is a big problem, and so one of the things that we're doing, and I see Bob LaFaro back here is helping build these. We're actually building a roughly 1 megawatt grid-connected solar research array here on site, just across the street from NSLS2. The reason that this is different is that most solar facilities are what are called net metered. So if you have a solar panel on your house, it's very unusual for you to be able to use that power. Only thing it does is run your meter backwards. In fact, the National Renewable Energy Laboratory has a large set of solar arrays all around, and all it does is run their meter backwards. If you really are interested in grid integration problems, you need to figure out, is there a way that we can take this 1 megawatt and use it to power the site? So we're actually going to use that 1 megawatt as a mechanism for testing schemes for integration into the site. And we've promised on a stack of Bibles to Mark Toscano and the people that run RIC and NSLS2 that we're not going to screw up the energy that's going to them. In fact, we hope to fix it in some ways. So storage is something that I've mentioned. We didn't get a hub, but I think we have a promising future. I don't know how many of you had a chance to meet or talk to Esther, but I think that what we built here with our assets and Esther owns about half a floor over at the Advanced Energy Center at Stony Brook as well. These are remarkable facilities, and we're kind of building up what eventually I think we're going to call what we are calling a solution center here on site. And I'm sure Jim Misevich will be down here talking sometime, and I'll let him expand on that. But storage is one of these ways that you can, in fact, enhance your ability to match supply and demand. So in this context, one of the things that we've realized, and we're not quite sure whether it's a Northeast or European or generally true, but the idea is that most microgrids are like Silicon Valley. There are companies like Intel who consider the grid to be so unreliable that they have their own generation, they have their own power conditioning, and they have the ability to completely disconnect from the grid. That's a classic microgrid. During Sandy, Stony Brook disconnected from the grid, cranked up their coal-fired power. I think it's coal, isn't it coal, Dune? I think coal or diesel, something. Their fossil fuel power plant, and they were up. They ran isolated from everyone around them, and people lived over there, went there and charged their cell phones. Dune charged his cell phone on the Stony Brook campus. So that's a classic microgrid. But what we believe is that you can manage small portions of the grid in order to optimize the benefit for the grid. You can optimize the benefit for the customers. And we've kind of come up with this morphology. And the thing we're starting to talk about are dynamic microgrids. And this is a complicated diagram. I'm not going to what I'm going to do is point out a couple of things. AHBL means all hell breaks loose. This is when the hurricane hits, and you go from all the customers up here to down here. And the question is, how do you get back up to here? And so we've got a set of schemes on how we might use local generation assets and so on in order to, one, decrease the number of customers who are affected immediately and increase the rate at which customers, in fact, are being restored. And we're in the process of testing this out. And I'm not going to go into, I'm happy to talk about this, but that's another hour. So last thing I'm going to do is I'm going to touch briefly on efficiency, biofuels, and nuclear energy. And so where's Bill? Bill Horak, where's Bill? Bill will tell you about anything that I didn't talk about in nuclear power. You just grab him afterwards. But anyway, I'd like to highlight a couple of things. One, in terms of discovery to deployment, is the famous Tom Butcher story. This is kind of interesting and is one of the major accomplishments, I think, of the laboratory in this domain. Tom burns stuff. You know, that's kind of his job. He burns oil, he burns, I think he's burned turkey renderings. Currently he's burning wood over in 526 to kind of test wood stoves and things like that to see if they meet environmental requirements. In the 90s, through LDRD and so on, Tom developed an alternative burner technology that eventually, through this collaboration, was put into widespread use. And we've tried to validate these numbers, but the estimate is that it probably saved the American public $25 billion in fuel costs since its deployment. And that's kind of remarkable. That's smaller than the budget of the laboratory over the whole period of time. So the ROI here is really pretty good, and he didn't get much out of that. In fact, his lab looks a little shabby, but we'll get it fixed up eventually. But at any rate, this is kind of the sort of thing we've done, one of these untold stories. And that's one of the interesting things in GARS is there are a lot of individual investigators. We don't run big experiments like RIC or run a big facility like NSLS. We have a lot of small things. And in the same way that the guys on the individual beam lines at the light sources generate the science, our labs generate them in small science. The next one is one that's in progress right now. Over in, I need to pray, it's EBC now? Is that right? EBC? The folks over there are trying to alter the biomass structure of potential fuel crops. And what we do in GARS is we're examining thermochemical conversion of biomass. Everyone's heard about ethanol production and things like that. It's kind of a low temperature path to ethanol. And most of the Department of Energy's investment has historically, at least for the last 15 years, been in kind of this fermentation process that if yeast is good enough for beer, it ought to be good enough for fuel, right? I mean, that's kind of the view. But Suresh Babu and Ofe's here, right? There he is, are working on trying to understand what biomass can be used for. It's not necessarily for fuel. It can be used as a feedstock for chemicals and so on. And they have an analytic capability to do that and says, well, here's an interesting feedstock. Then they kind of carry on. They get this analysis right here that says, what are the things that come out of this high temperature conversion process? Then we go talk to the folks over in BES and see if there are, in fact, catalysts that can make that more economically valuable. This is kind of our vision of the future in that regard. And I think it's got a lot of potential associated with it. And then finally, the last thing I'm going to talk about is materials for the next generation of nuclear power. And every time I walk out and see the Brookhaven Graphite Research Reactor on the Hill, I realize how important we've been in the history of nuclear power along the way. And this particular facility that we're talking about putting at NSLS2 is really the continuation of that. But basically what we're trying to do is understand the radiation effects of materials. And I think I saw Lynn come in. She can correct me. I'm sure Bill can correct me if I'm wrong. But one of the interesting things as you go to next generation reactors is the materials have to withstand over their lifetime greater and greater amounts of radiation, which can be translated into how many times does each individual atom in the material get displaced by a radiation event. And typically that's in the low tens right now in a typical reactor. We're going to start pushing 100 when you start looking at fusion. So how does a material maintain its integrity when every atom in it has been hit by some radiation event 100 times over its lifetime? And so the question is, how do the materials recover? That's really the question. And so this particular facility here is designed to do that. Here are ion beams simulating what happens inside of the reactor environment, going against a sample, and then we use X-rays coming out of NSLS in order to characterize the materials and their recovery from the radiation event itself. It's really very cool. And one of the nice designs with NSLS is we can put this little building well away from the ring, so we can look at materials that are not only fresh materials, but materials that may have been irradiated under other circumstances. So it's a kind of a remarkable thing, taking advantage of a remarkable tool. Again, in the spirit of discovery to deployment, we have this ability to kind of drive this whole process, not only with the discoveries we have here, but the tools. So that's just an introduction. Thank you. Questions? Oh, come on. Yes?
You talked about the electric grid infrastructure. How much loss do we typically have in generated power getting to where it's used?
I couldn't quite hear the question. Can we get his hot mic? Or you can come down and we can talk.
This way.
Yeah, okay. I'll come closer too.
You talked about the electric grid. Typically in our present grid, how much loss do we have of the power going from generation to use?
So that is the heart of the economic value of this, in our view. The canonical numbers are that between generation and use, 9 to 11% is lost. Roughly a third of that is in the transmission, which is what connects the big generators to the local distribution system, and the remaining 2/3 is inside of the distribution itself. Now that's a number that is actually highly variable, there are two things that are important about it. In Staten Island, the local distribution loss in the summer sometimes is as high as 22%. 22% of the electricity, it's like pouring money on the ground. And it happens because the conductors heat up and the equipment doesn't perform particularly well. You know, those of you who have hybrid cars know your batteries don't work well when it's cold. Well, the electric grid loves it to be cold. They can't stand it to be hot. And so that's a problem. But there is no economic incentive for utilities to fix that, because it's written right into the rate base, and they just put their number out and they get paid for that. And if they improve the performance, all it does is they get less money next time. So there's no economic, rate cases every 3 years, so they might get, if they get it paid back in 3 years, they get no benefit. If they get paid back in 18 months, they might get a little bit of benefit along the way. So we're looking at not only the technology to fix that, matching phases, improving the power factor and things like that, but also trying to, since I'm the head of the New York Energy Policy Institute, we're actually looking at how to change the nature of the rate setting process to incentivize improved efficiency in the grid. And when Pat Looney and I did the scenarios for the 80% reduction by 2050, one of the assumptions we made was we could cut the loss in the grid by a factor of 2. So it's a big target, it's an important target, and we think our work on the distribution system is going to lead that, and we've got a utility upstate in Orange and Rockland counties that's done some remarkable things with smart grid technology to make that happen. Great question.
Can I just ask a follow-up? The 2/3 loss in the distribution also associated with transmission, just locally?
Well, so the distinction between transmission and distribution is kind of a voltage level sort of argument. And so where you draw the line is what leads to the distribution. So almost all thinking about the grid is driven by the guys in the West, where there's a kind of a clear distinction between those. And those are the numbers that I'm talking about. Here we're much more interdigitated with transmission, distribution, sub-transmission, super distribution. They got words for it all. But the critical thing is that from the size of the transformer we have outside the gate to inside of here is where at least 50% of the loss takes place. Bob.
Sure. So Enroll in Colorado and Argonne Lab are looked upon as the DOE laboratories of renewables applied. How do we get on the map?
We say we're from New York and we're here to help you. It's kind of the way it goes. It's really it's interesting, and the sociology of grid research and renewable energy research over the period of time since the Department of Energy, and you've been in the middle of it. So, but I think the grid is dominated by Western thinking. In fact, all this stuff with ISOs and things like that is driven by the West. I think the Office of Electricity is looking to insight into the Northeast. The next is that Argonne, for example, is known for battery research. They won the hub, and they've been working on automobiles for a long period of time, and that's an important goal. But grid-connected storage in the Northeast is a critical factor, and we really are in a better place to take advantage of that than the others. Our relationship with the Photovoltaic Manufacturing Consortium is incredibly important, and using the same kind of techniques that Ralph James has used for improving the crystalline material for CZT detectors, we think we can make a tremendous improvement in the manufacturing of thin-film photovoltaics here. So it's not as though all the niches in the ecosystem of energy are filled. We have chronically underinvested in energy research, energy development, and energy deployment, and so my sense is that we don't have to compete, we can cooperate, and there's plenty of good problems out there to do that we're uniquely positioned to do. Mark?
Gerry, are we getting any closer to the viability of hydrogen storage as a practical?
Wow.
I don't mean we, just the lab.
No. Well, we're one of the central players in doing that process. So I believe, and Bill, I think you may have heard more about this. The U.S. government basically has said they're going to store hydrogen by compression. So the interest in the kinds of things where we've kind of developed exotic materials for hydrogen storage, there's less interest. Where's Fong Wong? I saw him come in. Isn't that right? I mean, that's kind of the conclusion. There's a lot of good stuff, a lot of good technology, I think, that's possible here. But I think that the hydrogen economy is on a somewhat slower path. And I think that if we want to increase the pressure back to different kind of storage techniques, I think we have to drive fuel cells. And here at the laboratory, I think the stuff that the catalysis guys have done on reducing platinum loading and things like that, I think we're going to try to push in a direction where we're going to try to turn those things into the appropriate membranes and things like that. I think there needs to be a drive from the demand side before there'll be a rekindling of the interest in hydrogen storage. And that demand, I think, is fuel cells, at least for transportation sector at this stage. Yes?
I think one of the important factors in ensuring the reliability and availability of the grid is defending it from cyber attacks.
That's true.
Like the one that happened in South Korea.
Yep.
Does BNL have a role in defending the grid
Yeah.
from this kind of cyber attacks?
We're almost all of the current cybersecurity things for the grid have focused on defending the information infrastructure that controls it. And we have very little involvement here at BNL in that aspect of that. And it turns out, though, that Stony Brook at the Center for Excellence in Wireless Information Technology, CWIT, has a large program in that particular area, and a strong connection to Computer Associates. And so a lot of people worrying about it. NIST is the leader. The thing we're doing is a little bit different than that. As it turns out, one of the most interesting things to me in the grid is that they model all the time. They do dynamic analyses and they do this thing and that thing. But they don't believe the model. The model, from the standpoint of the operator, is used to fill in gaps where the data isn't. So, and the models that are being used typically are not considered good enough for you to say, here's what I measure, here's what I model. is the different, what can I learn from the difference between the two of them? They don't believe the models well enough to believe that the difference has a lot of value in it. We've been working on a modeling scheme here, working with a professor from Virginia Tech, Robert Broadwater, that has a much more detailed modeling scheme, very geographically based, consistent with what's going on. And we have evidence in working in Orange and Rockland that the model is good enough to compare with the data, and that the data is in fact meaningful, and the model is sufficiently accurate to tell you something squirrely is going on in the grid. They've used it for diagnostics on failed components or missteps or incorrect data being put into the model. The model's quite robust in that regard. So I think the vision we have right now is that perhaps through this modeling scheme, we can model the grid in real time. And if something starts to happen, you don't have to tell by the penetration. You can tell by the consequence on the grid before you get into a cascading failure and do the kind of things that are in fact necessary. The current cybersecurity strategy, not exclusively, but almost all of it is a barrier strategy to protect the infrastructure and detect intrusion, much the same way that we do for our own grid here. I think there really is a way to use the grid itself as a sensor of things that, in fact, may be untoward. And it also allows you, I think, to do a better job of getting ahead of events like the one in 2003 and figuring out what to do with that. So we're not really involved, but we think we have a path that we are setting up our hot dog station where we think the parade of cybersecurity has to go by at some point along the way, and that's the use of models.
You mentioned the growth at the beginning, so this is certainly an area that the lab is growing into. Mm-hmm. So how well are we doing in terms of reaching the goal of the growth, and how is this the size you want to be? And
I'll give the answer I gave Bob yesterday when we were talking about it. We have managed to make up for $30 million worth of loss from the environmental management program over the past 2 years. Now, that's a big deal in terms of the size of the laboratory. I think that in terms of the growth of the lab, there are kind of three things that are important. First off is it's not just going to happen in a single directorate. It's going to have to be all the places in the lab. The Office of Science in that is probably, we have that market, I won't say completely saturated, but I think we can predict that's going to be in the future. So I think the next step, I think we develop an understanding of how customers come to us naturally and the effect of our marketing. I think the thing we have to do right now is we have to set real goals. I mean, that's what we're doing in national security. We think that the kind of contribution we've made in nuclear, for example, might be applicable to non-proliferation of chemical weapons, which is a big issue out and about. I think the work that we're doing in the grid might be something. We've got stuff going on in BES around solution centers, the ability to be able to attract people here to take advantage of NSLS2, the building of medical accelerators and the accelerator research that's been happening in CAD. And I think right now, I think that we have a good appreciation that needs to happen. I think we need to put a little bit more intent behind it. And I think that's what's going to happen over the next while. So far, I think we have systems in place where it's a lot easier for external customers to work with us. That's a good thing. I think we have a little better understanding that the best effort cost incurred mentality that's typical for Office of Science is not necessarily what a drug company or an electric utility would like. They'd like a real product delivered on time, on schedule, on budget, as promised. So I think we're in a way going forward. So I'm pretty confident we have the base built. Now it's just a question of getting the intent moving forward.
What kind of lab revenue of that?
That's a little bit complicated. Let me. The aspiration is that we would like to have 20% of the lab budget come from work for others, Homeland Security, or CRADAs, the stuff we do with the private sector, and then 20%, a matching amount of money, come from the non-Office of Science DOE mission folks. So EERE, fossil energy, nuclear energy, NNSA, to name most of them, I think. And currently, we're at about 30% in that number, and it needs to be 40. But at the same token, the laboratory itself has to grow. And so that's part of the question. We have a certain amount of numerology that we need to do. And it's not clear. I mean, when we had $30 million, which is 5% of the volume a few years ago, just coming from EM, that's not the science work that we're doing. Our budget, Randy does really important work here, but it's not the science work of the laboratory. That's part of the research, part of the volume of the laboratory as well. So we have to be focused in that particular direction. So my guess is that we have to double work for others and increase the non-DOE portion correspondingly. So, Dune, do you want to? Is that fair? Okay. Time for one more question. Yes.
Could you talk a little bit about renewable energy storage for the homeowner and where it's going?
Yeah. So the question is in support of the homeowner and renewable. So I think they're the most popular and probably most appropriate renewable energy, unless you own a farm, is probably solar. And there are three things about solar for the residential customer that's important. The first one is that I think the cost of the systems are going to come down, and these thin film technologies are one of the things that's going to make that happen. The second thing is that increasingly we're going to see solar materials built into building materials like shingles and things like that, which if you're building a new house or you have to replace a roof may in fact be important. That's been 5 years and a $50 million investment away for at least the last 10 years. So I'm not holding out a lot of store on that one. Isn't that kind of the right scale, Bill? Yeah. It's a little bit of a holy grail to get so that it's durable and can serve the dual purpose. The third thing is, depending on where your house is and what your reliability is, it's really very much a local economic decision that you're making. And there are incentives and all that sort of business. I think NYSERDA's got a nice tool to help you figure out whether it's a good deal for you or not. But right now, I hate to say this because I think subsidies are the crack cocaine of the renewable energy industry. I'd wait for an incentive before I put solar up here. Yeah.
And how about energy storage for existing homeowner technology like a solar?
Well, I think that's we actually believe that kind of smart houses are even more important than renewable energy. How do you buy electricity high and low? There's a thing called a double auction where you say, well, I'm only interested in running my dishwasher if I can get my power for 6 cents a kilowatt hour, and you kind of wait and you don't get started until someone will offer to provide the electricity for that period of time. I think the smart technology, we really haven't figured out how to do it, but I think that there's a certain amount of empowerment that may come from the ability to be able to manage your demand in order to be able to take advantage of varying prices. Currently in the state of New York, it's illegal to use time of day rates for residences. And so that would have to change. You'd have to have the tools to be able to work that out. California is experimenting with that. They're on a path for Enron-like conflagration in that domain too, I think, but we'll see how that all plays out. I think there's information technology, the ubiquitousness of it is important, and I think there's a real potential for that. And there's a little bit of work going on here, but our work is mostly focused on bigger buildings like ours. So, okay, thank you again.